Good morning. Today we will discuss about the detection of external and internal faults on bus bars and the impact of the CT saturation on detection of external and internal faults. In the last lecture, we have discussed about the common mistakes which we do when we select CTs based upon their CT ratio. We have seen what is the correct method for selection of CT ratio, and we have finalized the formula for ideal CT ratio. And the formula for ideal CT ratio was maximum of all the available feeder current ratings or feeder currents by 1 ampere or 5 amperes. This is the ideal case for us, right? So based upon this, we have decided the formula for ideal CT ratio. And in today's class, we will see how the detection of external faults and internal faults is impacted by faulty CTs, and in particular saturated CTs. So I hope that by the end of this lecture, you will be able to describe the impact of non-ideal CTs, or in our case, we will consider what is the impact of saturated CTs on the external and internal faults on the bus bars. So I will start with the types of faults on the bus bars, and then we will see what a non-ideal CT is. And then we will see the behavior of non-ideal CT for external and internal faults. So let us start with bus bars. We have discussed in the last week that bus bars are critical components of electrical power systems. They serve as major conductor or the main conductor for distributing power to various components and loads in the system. It is just like a joining point where so many wires are connected, or what we call in electrical terms as feeders. So let us suppose this is an incoming feeder and these are different loads. So this one is called as a feeder. So a feeder is basically acting as a major conductor which distributes power to different loads and different components of your power system. And it can experience faults which may affect the reliability and safety of your power system. And in particular, there are two types of faults which do occur on the bus bars. One is an external fault, the other is an internal fault. And we have already discussed that differential protection is commonly employed for bus bar protection. So this is my bus bar and this is my incoming feeder, and I'll take 3 outgoing feeders. Each one is providing to a load. So normally I do employ right. So this is my operating point. So this is my operating point. Okay. So this is the differential scheme. So this is the bus bar. So these are on one side and these CTs are on the other side. So based upon the difference between, let us suppose if I take it as IA, IB, and there are so many things here, right? So if IA is not equal to the combination of IB plus IC plus ID, because this is the incoming current and these are the outgoing current. So based upon that, if there is a difference between these two, then automatically the relay will operate. So based upon this protection scheme, we do classify the faults as external faults and internal faults. external faults are those faults which do happen on external side of the CTs. So this is the zone. So this zone, wherever the CTs are there, beyond the CT. So if a fault occurs in this zone, it is called as an external fault. And if your fault is occurring in between this zone, between the CTs, then it is called as an internal fault. So this is the classification which I am making in this case. External fault and also internal fault based upon my present location of my CTs. Okay, so these external faults, as I have already shown you, now let us suppose this is my only two feeder system where this is the incoming one, this is the outgoing one. Now let us suppose these are my CTs. Okay, so external faults occurs when there is a fault in, as I already told you, right? So this region and this region. So external fault occurs when there is a fault in an external component connected to the bus bar. See here, these are all the external components. This is an external component, this is an external component. When there is a fault in the external component, then it is considered as an external fault. Maybe most probably there is a fault in the generator, fault in a load, or fault in a transformer which is connected to this one. So all these will result in external faults. So if external fault occurs, let us suppose if this generator is shorted, or if the load is shorted, or if this transformer gets shorted, then automatically what happens? There will be a huge current flowing in. Let us suppose if this is shorted, right? So huge current will be flowing in the bus bar. So where this is current coming from? This current is coming from this one, right? So this is the current. So which means that through the bus bar the current is flowing, and hence there will be a huge amount of current flowing in the bus bar, which will result in high currents. If there are high currents, then automatically what happens? There will be high temperatures releasing. So this will lead to thermal stress, and ultimately it will damage the bus bars. So external faults can result in high currents flowing through the bus bar, leading to thermal stress and physical damage to the bus bar. Whereas internal faults, on the other hand, I'll take this as a bus bar, okay? So internal fault is fault which is happening in this region. So internal faults occur within the bus bar itself. So these can be because of various factors, most probably. So most probably this bus bar has experienced an insulation failure, or maybe there is a mechanical stress, or maybe because of the overheating of the bus bar it has burnt out. So because of any of these reasons, the fault might have occurred internally. Okay, internal faults lead to short circuits. Here also there will be a huge currents, but the fact is that the currents will be flowing in only one of these sides, not on the either side. So this will cause damage defaultly to the other components which are connected to this bus bar. So these components, or let us suppose if the fault is in this way and the generator is present here, so these will carry huge amounts of current. So these may get damaged, while the other one will be safe. So differential protection is exclusively employed for detection of internal faults. See, since only one side of CT, only one CT is experiencing a current, the other one is not experiencing. So defaultly, there is a difference in the currents, I1 minus I2, right? Then automatically the relay will operate, right? So we have seen that in the last week, the differential protection is employed for detection of internal faults, not for external faults. For external faults, the differential scheme relay is non-operative. Now, what happens when there is a non-ideal CT which is present there? So, normally when during selection of the CTs, when we are designing a system, we feel that those are the ideal ones, right? So, normally all the CTs are assumed to be ideal, but when the CT primary currents or the burden on it is within the limits, the CT will be behaving like an ideal one. So normally what happens is, let us suppose if there is a line which is carrying 2000 amperes of current. So I do have a CT, let us suppose its ratio is 500:1. Right. So normally what is the secondary current which will be flowing in the circuit? It will be 4 amperes, right? So it is the ratio which is to be maintained, right? So if the burden is within the limits, then automatically it will be working as an ideal one. Now, if the primary current exceeds the design value of the CT burden, let us suppose if the current is too large enough, maybe it is 20,000 amperes. So what will be the current? It will be 40 amperes. So in that case, the CT burden may be excessive. So in that case, the CT will not act as an ideal transformer, but in fact it acts as a saturated transformer. So instead of getting 40 amperes here, I may get a current which is very low when compared to the desired 40 amperes. And this type of behavior, it has very serious implications in the protective schemes that we will see now. So what happens when these non-ideal CTs, which means the saturated CTs, are present? So now in this picture, if you carefully see, this picture has been taken from the textbook by Dunker and Bind. All the pictures have been taken from this textbook. You go through the textbook. So this is the case. Now see here, there are two incoming feeders, each one carrying current of 10,000 and 20,000 amperes, and this is my bus bar, and this is my external feed, outgoing feed. And see the current which it is carrying 30,000, right? 10,000 plus 20,000 incoming, which is equal to 30,000. Now this is my CTA, CTB and CTC. So these are the lines, A line, B line, and this is C line. Right. So CTs are present. So all the CTs are of the ratio of 3000 by 1 because this is the highest one. So based upon that, it have been selected. So normally the current which will be flowing is 3.3. This is 6.6, and this is what current must be flowing? The current, since it is 30,000, what is the current which is to be flowing here? It must be 10 amperes. But unfortunately, assuming that this is saturated. Earlier case, if it was unsaturated, what was the current here? 3.33 plus 6.66, and it was 10 amperes. See, this is 10 and this is 10, so relay will not operate. But if this is saturated, I'll check, let us suppose instead of 10 amperes, it is allowing only 4 amperes of current. Right? This is 10, this is 4. See, there is a huge difference. So automatically what happens? There is a current, 6 amperes of current. So automatically what happens? The relay will operate. Normally for external ports, the relay shouldn't operate. But here in this case, what is happening? Even though if there is an external port, the relay is operating because of the saturation of one of the CTs. I am assuming that only one CT is saturated. A and B are not saturated because they are carrying less amount of current when compared to this. So since it is carrying huge current, there is a higher probability of it getting saturated. So it has become saturated. So because of the saturation, it is allowing less amount of current, and because of this, even for external faults, my relay is operating. Understood? So a saturated CT may falsely give an alarm for external fault also because of the presence of saturated CTs. Now see, I am considering an external fault. This is the explanation which, see, consider the external fault beyond CTC. The CT on the faulted feeder has to carry the sum of all the current. So how much current it is carrying? 30,000 amperes it is carrying. It is a very large primary current. So either CTA or CTB, they are carrying only 10,000 and 20,000 amperes. So defaultly there is higher probability for CTC to get saturated. So assuming that it is faithfully transforming, but it is not actually transforming. So that's why instead of carrying 10 amperes, it is allowing only 4 amperes. So which means that incoming side it is 3.33 plus 6.66. But here outgoing feeder is providing only with 4 amperes. So there is a difference of 6 amperes, which we call it as a spill current. So this causes the scheme to maloperate. It loses ability on external faults. Understood? In the worst case scenario, CTA and CTB, they continue to transform faithfully as per the nameplate CT ratio, but CTC, which is carrying the total fault current, gets completely saturated, which indicating an imbalance in the transformer secondary currents, resulting in substantial spill currents. So that's why if there is a saturated CT, the operation of a differential scheme under external faults is clearly a case of maloperation. Whereas in case of internal faults, now let us suppose even though it is saturated, assuming that it is saturated, since a fault has occurred internally, so this is 10,000 amperes, this is 20,000, so 3.3, 6.6. So here a fault has occurred internally, so there won't be any current here, there will be zero current here. So here 0, here 3.33, so 10 amperes will be coming. So defaultly there will be a spill current of 10 amperes, and this is what the relay should operate. So the relay is operating healthily for internal faults, and this is what its fundamental job is. So for fundamental job, it is satisfied. But another fundamental job is it should not respond to external faults. But because of the presence of saturated CT, it is responding to internal faults. So the maloperation of busbar differential scheme on external faults is caused due to non-ideal behavior of CT carrying excessive primary currents. Understand? This non-ideal behavior of CT, this causes maloperation in case of external faults. This is a conclusion. So what should we do whenever we are erecting the CTs? We should take care of whether it is saturated or not. Okay. So I hope that now you have understood what is the significance of saturated CTs on the external and internal faults of the busbar. Okay. So in the next class, we will see how to represent a saturated CT for our analysis. Thank you.